Hello and welcome. This is going to be a video walkthrough looking at a Desmos lesson that you can do on your own. It is also nice to do collaboratively in a class, but we're going to see how you could do this lesson on your own here. So I'm going to click Start Activity. What I see in front of me is an interactive graph here where I can kind of move some things around. And I'm asked a question, what kind of triangle is it? Is it acute? Is it right? Is it obtuse? Now this is something that's not new information. It's reviewing some old information. Remember that a right triangle has a right angle. So when I look at this triangle and I see that there's these angles and these side measures and all that kind of stuff, this looks like it would be a right angle, so I'm going to see if I can test that out. The big square has a 13 in it. That means that the square is 13 square units. The medium square would be a 9, and then the small square would be a 4. And I get a green check mark, so that's good. Let's see if I can make like an obtuse triangle. So I'm trying to move some things around and make some kind of obtuse triangle. That kind of looks like an obtuse triangle there, where the angle looks bigger than 90 degrees. And I noticed that the big square is 17 and the other squares are 8 and 5. That totally works. Now I need to make an acute triangle. So an acute triangle is when the angles are all less than 90. That looks less than 90, that looks less than 90, that looks less than 90, all the way around. I may, for another version of this activity, make it so that you can actually see what the angle measures are. Okay, the acute one here, the big square is 17, the medium square is 13, and the small square is 10. So here's generally kind of what's happening is that as we reshape this picture here, when these two smaller squares add up to the larger square, like 17, 17, and 34, that makes a right triangle. So in other words, this is the classic formula you've seen before, where a squared plus b squared equals c squared. We're going to kind of wrestle with this idea, but kind of expand on it so that you're not just looking about when they're equal, but also when they're not equal. So for example, here I have an acute triangle, and these two smaller triangles add up to 30, and the bigger triangle is only 20. So it's like the bigger triangle is a little bit smaller than the two other triangles put together. And so that's kind of interesting to think about what how those pieces fit together, which ones are bigger, which ones are smaller. Okay, let's accelerate here a little bit. We're going to have a couple of main categories. It's either a right triangle or not a right triangle. The right triangle has that formula, a squared plus b squared equals c squared. And then not a right triangle is where they don't add up together. Okay, so 16, 16 makes 32. That's one of my right triangles. 8, 5 is 13. That does not add up to 9, so that's going to be not a right triangle. I also have these two formulas here. A squared plus b squared is either bigger or smaller than c squared. Now this one's kind of interesting. It's isosceles, but it's not a right triangle. That's clearly, if I were to click on here, this is clearly bigger than 90 degrees here. It doesn't have a perpendicular intersection. And 36 is not the same as 26. So that's going to be not a right triangle. Now here I have another isosceles, but this does look like a right angle perpendicular intersection, and 10 and 10 do add up to 20. They are equal, so that is a right triangle. Here I have another right triangle. 9 and 81 do make 90. 29 is not the same as 10 and 17. So that's going to be over here. I do notice that as I'm adding things together, it'll tell me how many pieces are correctly matched. I'm not sure that it is perfectly matching up, so I might have some errors in that, but we will see. There we go. So those should all be matched. Maybe there's one in here that is off. Let's see. It was that one. So this is not a right triangle. That's an error in the answer key, but it'll be fixed for you all. There we go. It was left by itself. But it's definitely not a right triangle. Okay, let's click next. So right triangle sides, this is a right triangle. We call this side across from the right angle, the hypotenuse. It's the longest side, and the other two pieces are going to be the legs. This is a quick identification to try and see which pieces go where. The hypotenuse is there across from that, and there's the long leg. And when you get the three pieces in the right places, you'll get a little thing that says, well done. All right, so I know this formula. We've seen this before, and it's like a squared plus b squared equals c squared. So a and b are my 3 and 4. So I have 3 squared plus 4 squared equals c squared. But another way to to say that is I could square root this piece here. So I could have 3 squared plus 4 squared inside the square root equals the c. That's another way of writing the same thing. So I'm just going to write that. The square root of 3 squared plus 4 squared. When I click submit, it says, yay, I got the right answer. I can also use this calculator here to do some of the calculations if I don't want to do it in that place there. So essentially we have this idea that these 3 squares have a relationship. The 9 and the 16 add up to the 25. Let's take a quick commercial break to talk about why do we call it the Pythagorean theorem. We don't call it the Pythagorean theorem because Pythagoras discovered it, but instead he just kind of put his name on it. So what really happened historically is that Egyptian mathematicians were earlier to it. They knew of the theorem, though that's not what they called it. Pythagoras himself, the Greek mathematician, he believed to have studied in Egypt, so he learned it from them, and then he probably just labeled it with his name and a pattern. So what did they do originally? They took a rope with 13 knots on it. If you notice here, 3 plus 4 plus 5 adds up to almost 13. It makes 12. So the 13 is the 1 and the 13, the first knot and the 13th knot kind of overlap and count as like the beginning and the end, so it counts twice. But then that triangle would be stretched into a right triangle if you stretched it out and held it in the right places at knots 4 and 8. Just a little history lesson there. So this 3, 4, 5 triangle that makes a right triangle, just a classic combination where the Egyptians did it before Pythagoras, but Pythagoras has his name on it. So let's do some more. Here we have another calculation with 8 and 15. So I know that 8 squared plus 15 squared is going to equal c squared. Let's kind of do this in a couple of steps here. So I'm going to write 8 squared plus 15 squared. And then I need to square root that because that's 289. So if I say square root of 289, that is 17. Submit, and it's correct. Okay, now this one's a little bit different here. If I were to think about this, I'm going to have like x squared, or that leg squared, plus 12 squared equals 15 squared. So I want to rewrite this a little bit so that I get that x by itself. If I were to use math.new, I could do the same kind of thing. I could say x squared plus 12 squared equals 15 squared. And I can square the 12, I can square the 15, I could subtract 144 from both sides. And an easy way to undo squared is you can drag the 2 to the other side, and that'll say, do you want a square root? Yes, I do want a square root. So the square root of 81 is 9. Now this says plus or minus 9. We're not going to, negative 9 times negative 9 is 81, but we care about the positive 9 because we're talking about positive measurements. So this would have been a 9 there. Now if I wanted to do that in this calculator, I would have said 15 squared minus 12 squared if I'm finding a leg. And then I need to square root the 81. Both ways would have worked. So it's sometimes helpful to know common integer numbers that fit this pattern where you don't have to approximate it with a decimal or write it in a square root form. But common triples you'll see are 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25. But other versions of those are those same numbers, but just multiplied into bigger multiples. So these first 3 here are just multiples of the 3, 4, 5. So 3, 4, 5 doubled becomes 6, 8, and 10. 3, 4, 5 tripled times 3 is 9, 12, and 15. And then times 4 would be 15, 20, 25. Those are just really common versions of the Pythagorean theorem where you don't have to, the numbers just come out with nice integers. Okay, here I have a triangle, and I notice that it's kind of upside down where the hypotenuse is down here. And if I'm thinking about this, I would have 4 squared plus 8 squared equals c squared. So then I can do that in a couple of steps. I'll say 4 squared plus 8 squared is 80. Then I'll have square root of 80. All right, now I can write my answer here in a couple of different ways. I'm going to type it once as square root of 80. And the second way, I'm going to kind of round it off. So it says 8.94. And there we go. So we'll round it off to a couple places. Let's try another one to look at. We have 12, 8, and x. Now, if you remember when you're finding the leg instead of the hypotenuse, you're going to take that big number hypotenuse and subtract the leg. So it's kind of like saying c squared minus b squared equals a squared. So that's square root of 80. And then if I find square root of 80, that's 8.94 again. Oh, that was 12. I should have said 16. So that's 192. There we go. So the exact length, I type in SQRT to bring up the square root button. 192. That is good. And that approximates to about 13.85 or 86. And this will give a correct answer. We'll take a look at why that's not working there, but it's, because it should be a 13. There we go. So even if you said 13.5 or 13.86, either one of those would have been correct. All right, now this one here, my question is it a right triangle? Well, let's check. I'm going to check the two smaller numbers and make them into squares. 6 squared plus 8 squared, so that's 100. And 9 squared is 81. So those two should have added up to the other square, but they don't. So no. 6 the hypotenuse would have been, I'm going to put square root of 81, or not square root of 81, square root of 100 for it to be a right triangle. Instead, it's square root of 81, which is too small. Okay, now this final one, hopefully you're starting to get a little bit more of an idea here, but the notes will help with this too. We have 3 groups that we're going to sort into, either right triangle, acute triangle, or obtuse triangle. So a right triangle is going to have an angle that's 90. The 2 smaller squares add up to the third one for c squared. And so that means like our 2 blue squares are going to add up to the green square. Let's see which ones do that. Well, the 10 and 10 make 20. That's good. And it says we have 4 out of 15, so we're on the right track. And let's see, we have 13. This one here looks like it adds up. 17 and 68 do make 85. All right, so we have one group done, 5 out of 15. Let's try the obtuse triangles. So obtuse triangles are when that green square is too big. So there's an obtuse triangle. And where else do we have it? We have it here. So that's our 2 kind of pictures. And one of the angles is greater than 90 degrees. That's true. Another way of thinking of it is when your C side or your hypotenuse side is bigger than the other 2 added together. All right, now all the rest of these just go into the last pile. And that's it. So we'll just put them all in there. And yay, they are all matched 15 out of 15. I'm going to pull this up a little bit higher. There we go. Awesome. So that is just this kind of quick review on Pythagorean stuff and looking at different types of acute and obtuse triangles as well. But you'll also have more information on that in the notes. Thank you.